Picture a table with millions of rows and a question. Find the one row for customer 107. With no help, the database can only do one thing. Start at the top and read every row until it hits the match. That is a full table scan, and it crawls, row after row. On a million row table, you might read a million rows to find one. The cost grows with the table size. Order n. Now think of a thick textbook. You would never read every page to find one topic. You flip to the index at the back, look up the word, and jump straight to the page. A database index is exactly that. A side structure that finds rows without reading them all. Two structures rule the database world, the B plus tree and the hash index. Let's build both. Let's pin down what an index is. It is a separate structure, living beside the table, that maps a search key, the column you look things up by, to where the matching rows sit. Think of each entry as a tiny pair, a key value, and a pointer to the row. Organized cleverly, those pairs let us find a key in a handful of steps, then follow the pointer straight to the row, instead of scanning the whole table. Here is the workhorse of nearly every database, the B plus tree. It is a balanced, many-way search tree. Wide and shallow, not tall and thin. Let me draw it, then name every part. At the top sits an internal node. Here is the crucial twist of a B plus tree. Internal nodes store no real data. They hold only guide keys, signposts that tell a search which way to turn. 30 and 50 here are pure routers. Every real key lives in the leaves, and only in the leaves. Read them left to right, and they are in sorted order. 10, 20, 30, up to 60. Each leaf also holds the pointers to the actual table rows. And notice these arrows joining one leaf to the next. The leaves are strung together into a linked list. That single detail is what makes range queries fly. We will use it in a moment. One more property, and it is the reason for the name. The tree is balanced. Every leaf sits at the same depth from the root. So whichever key you hunt for, the path down is the same short length. Predictable. Every time. Now the payoff. Searching. Let's find the key 40. The search always starts at the root and walks a single path down to a leaf, comparing at each node. At the root, we meet the guide keys 30 and 50. 40 is bigger than 30, but smaller than 50, so it belongs in the middle branch. We follow the middle pointer down and instantly ignore 2/3 of the tree. Down at the middle leaf, we find 30 and 40. Scan across. There is 40. Found it, following one path from root to leaf. 2 node reads, not a million row reads. And here is the headline. Because the tree is balanced and wide, the path from root to leaf is about log n long. So a B plus tree search is order log n, while the full scan was order n. On a million rows, that is roughly 3 steps versus a million. A single key is only half the story. The real magic is the range query. Let's ask for every key between 20 and 50 and watch the linked leaves earn there. Keep. First, descend to the lower bound. 20 is less than 30, so from the root we go left to the first leaf. That is where the range begins. In the first leaf, 10 is below our range, so we skip it, but 20 is in. Collect 20. 20 was the last key in this leaf, so we follow the leaf link. No going back up the tree, straight to the next leaf. 30 is in range. 40 is in range. Collect both. Follow the link once more. 50 is in range. Collect it. But the next key, 60, is past our upper bound of 50. So we stop, right here. And there is the answer. 20, 30, 40, 50. We touched exactly the leaves we needed, then slid sideways along the linked list, never climbing back up. That is why a B plus tree handles ranges and order by and between so beautifully. So why a B plus tree? and not the plain binary search tree from our trees lesson? The answer is disk. Every node read is a disk read, and disk reads are slow, so we want as few levels as possible. A binary tree splits two ways at each node, so over many keys it grows tall. Many levels, many disk reads. A B plus tree packs dozens, even hundreds, of guide keys into one node. High fan-out means it spreads wide and stays shallow. With a fan-out of a few hundred, a B plus tree over millions of rows is only 3 or 4 levels deep, 3 or 4 disk reads for any row. Keeping keys only in the leaves packs more routers per node, and the linked leaves keep range scans cheap. The second structure is the hash index, straight from our hash tables lesson. Instead of a tree, we have buckets. A hash function turns a key into a bucket number, and the key's row pointer lives in that bucket. Let's load 6 keys: 10, 20, 30, up to 60. Each one flies through the hash and drops into its bucket. And look carefully at where they land. Now an equality lookup, find 40. Hash it. 3 times 40 is 120. Mod 7 is 1. Jump to bucket 1, and there is 40. One shot. No tree to descend, no scan. Expected order 1. But now ask for a range. Every key between 20 and 50. Here the hash index falls apart. Watch where those keys actually sit. 20, 30, 40, 50. Scattered across buckets 4, 6, 1, and 3, in no order at all. Hashing destroys order. To answer a range, you would have to probe every bucket. A scan in disguise. Hash indexes cannot do ranges or order by, which gives a clean rule. If your queries are pure equality, find exactly this key. A hash index is superb, order 1. But the moment you need less than, greater than, between, or order by, you need the sorted structure, the B plus tree. One more distinction decides how an index relates to the table itself. Some indexes control the physical order of the rows on disk. Others just point at rows sitting wherever they already are. A clustered index stores the table rows themselves in index order, sorted, right there on disk. Because a table can only be physically sorted one way, you get at most one clustered index per table. Finding a row lands you directly on it. A secondary or non-clustered index leaves the rows where they are and holds pointers back to them. The rows can be in any order, a heap, and you can build many secondary indexes on one table, one per column. Now the catch, because indexes are not free. Every index you add is a second structure that has to stay in sync with the table. Reads get faster, but writes get slower. Every insert, update, and delete must update every index that covers the row. Rebalance the B plus tree, rehash the buckets, pay for the extra disk space. So the guidance is simple. Index only the columns you filter on, join on, or sort by. Your turn. Here is a query. Give me every row where age is between 20 and 30. You need to build an index on age. The question is, hash index or B plus tree? Pause the video and decide. I'll wait. Here is the reasoning. Between is a range, an ordered span of values, not one exact match. A hash index scatters keys and destroys order, so it cannot answer a range. But a B plus tree keeps its keys sorted in linked leaves. So the answer is the B plus tree. Descend to age 20, then walk the linked leaves up to 30. If you pick the B plus tree, you have genuinely understood the whole lesson. Trap 1, the big one. Treating indexes as free. They speed up reads, but every write has to maintain them. Index the columns you query, not every column. More indexes means slower writes. Trap 2, reaching for a hash index on a range query. Hash indexes do equality and nothing else. For between, less than, or order by, they are useless. Hashing throws away the order. Trap 3. The flip side. Because a B plus tree's leaves stay sorted and linked, ranges and ordered scans are cheap. One structure serves both equality and ranges. Trap 4. Expecting to clustered indexes. A table has one physical order, so only one clustered index. Everything else is a secondary index pointing back at the rows. And trap 5. Indexing a loss selectivity column. One with few distinct values, like a yes-no flag. It still matches half the table, so it barely narrows anything and isn't worth the right cost. Let's lock it in with numbers. A heap table of 200 blocks with no index averages 100 block reads. With a sorted file and an index, the same search takes about 5. 100 versus 5. That is what an index buys. So here is the whole picture. An index is a site structure mapping a search key to a row location. It turns a slow scan into a fast jump. The B plus tree is the all-rounder, balanced with every key in sorted, linked leaves. Order log end search, and ranges and ordering come along for free. The hash index is the specialist. Hash the key straight to a bucket for order 1 equality lookups. But it cannot do ranges. And it's always a trade. Indexes speed reads and slow writes. So index the columns you filter, join, or sort on, and no more. Get that balance right, and your queries fly.